In this lecture we are going to discuss on energy integral equation, and after that we'll see how can using this energy integral equation we can approximate the expression of the Nusselt number. So first write the thermal boundary layer equation, and that is is U del T del X plus V del T del Y, which is equal to alpha del 2T del Y2. Now if we integrate, so integrate this equation within thermal boundary layer, along Y, definitely from 0 to thickness of the thermal boundary layer. So if you do that, you will get integration 0 to delta T U del T del X into dy plus 0 to delta T V del T del Y into dy, and that is equal to 0 to delta T alpha del 2T del Y2 dy. Now from here we can write the first term, we just keep as it is, del x into dy. For the second term, do integration by parts, so that will be v into t 0 to delta t minus integration of t into del v del y, so del v del y into t del v del y into t into dy 0 to delta t, and that is equal to, on the right hand side it will be alpha into del t del y and 0 to delta t. So now to find out what we can do, let us see this term. So what is this term? Del v del y. From the continuity equation we can write this quantity is nothing but minus del u del x for 2D incompressible flow. So if you just put this quantity as minus del u del x, this minus and this minus will become positive, and we can club the first term and this term. So what we will get is integral 0 to delta t u into del t del x dy, that is the first term, and now you consider this term, and here also you see that it is integration from 0 to delta t, and it will be plus 0 to delta t del u del x into t into dy. Okay, so these two terms can be written under single integration, basically in this way. Okay, you need not to write this dy, and so we can write u into del t del x plus del u del x into t into dy. So we have taken these two terms, and what else is, that is plus v at delta t, and t at delta t is t infinity, that is at the edge of the thermal boundary layer, minus velocity y component of velocity at y is equal to 0 because of no penetration boundary condition is 0. So velocity at 0, y is equal to 0 is 0 because of no penetration boundary condition, and temperature is basically the T wall. Okay, so this part is not important, and that is equal to, here at delta T the temperature gradient will become 0, that means at the edge of the boundary layer temperature gradient will be 0, so that part will be 0, and minus alpha into del t del y at y is equal to 0, that will be there. Okay, so from here only thing that is required is you have to find out what is this quantity, and you can see this quantity can be clubbed together and can be written as del x of ut. So this quantity you can club together and you can write this quantity as del x of u into t dy integral of that. Okay, so this term, the first term, can be written in this way because this is the product of u and t, as you can see, and this quantity is somehow you have to find out, and that you can find out if you integrate the continuity equation within the thermal boundary layer. So let us see what we are getting from that. So the continuity equation we know is del u del x plus del v del y is equal to 0, and if we integrate this quantity, so del u del x into dy, and we are integrating within the thermal boundary layer, so 0 to delta t along y direction, and that will be is equal to clearly a minus of 0 to delta t del v del y into dy. Okay, so this right hand side term is a minus of v at delta t 0 to delta t, which is nothing but minus of v at delta t, and v at 0 is 0, so that term is not there, and here this quantity is 0 to delta t into del u del x into dy. Okay, so now you just put that value because the term is there from the integration of the thermal boundary layer equation, that is 0 to delta t del x of ut that we have seen just now, and then it was basically plus v delta t into t infinity. Okay, so v delta t into t infinity, so it will become negative because my negative v delta t is this quantity into t infinity will be there, but t infinity is a constant, you can put it under this integration or differentiation also. So del x of, you can write in this way, u into t infinity as if, okay, no problem, because t infinity is a constant. Okay, and this negative sign is because here it is negative, and so this is what is the second term, and that is equal to minus of alpha into del t del y at y is equal to 0. Okay, now from here what we can write, we can club these two into a single integration, that means integration of del x of what we can write, we can put this quantity first and then this quantity, then this negative will gone, so you can write this as u into t infinity minus t into dy. Okay, and that is equal to alpha into del t del y at y is equal to 0. Okay, and this integration limit is 0 to delta t. Now what you can do for this part, you can use the Leibniz rule for differentiation under integration sign, integration under differentiation sign. So if you do that, we know from the Leibniz rule, and according to that we know that ddx of integration of a to b some function which is of x and y into dy, and that will be equal to, we can write as integration of del f del x, okay, into dy from a to b, where a and b are only function of x, then plus this functional value at b, basically it is function of x and y, so at any x but at y is equal to b, into db dx minus fa into dA dx. So this is what is the Leibniz rule. So here what we are interested in is that f is equal to, in our case, if you see that we are interested in this quantity, so f is t u into t infinity minus t u into t infinity minus t. Let us consider this is our f, and what is a is 0, what is b is delta t. Okay, so then you see what is this quantity. So what is fb? F at b, that means f at delta t. So this quantity at delta t, it is clear that the temperature is T infinite. So fb is equal to u into T infinity minus T infinity, so that is 0. And if a is equal to as u is equal to 0, so fa is equal to 0 into T infinity minus T wall, so that is equal to 0. So it is clear that this term is equal to 0, this term is equal to 0, though, so we can say these two terms are basically same. So what we can do is that we can write this quantity as ddx of integral of this quantity. So we can write that ddx of integral u into T infinity minus t into dy from 0 to delta t is equal to alpha into del t del y at y is equal to 0. Now what we can do, we can express this temperature in terms of non-dimensional quantity theta. So if we do that, then let us define theta. So let us do it in the next page. Let us define that theta is equal to t minus t wall by T infinity minus T wall, and the expression is ddx integration u into T infinity minus T infinity minus T into dy is equal to alpha del t del y at y is equal to 0. Now it is clear that we can write T infinity minus T, this quantity, as T infinity minus T wall minus of within bracket T minus T wall. Okay, so that is T infinity minus T. Now we divide this quantity by T infinity minus T wall and multiply by the same T infinity minus T wall, so it will remain same. Now this quantity is nothing but now 1 minus T wall by T infinity minus T wall, which is theta, into T infinity minus T wall. Okay, so this bracketed term you can understand is nothing but 1 minus theta into a constant quantity, which is T infinity minus T wall, that can be taken out of this integration and differentiation. Okay, so and in the right hand side term, that is what is del t del y at y is equal to 0, that we can write as, if you differentiate from this equation, so alpha into del t del y at y is equal to 0, del t del y at y is equal to 0 is nothing but alpha into T infinity minus T wall into del theta del y at y is equal to 0. Just simply, if you differentiate both sides partially with respect to y, you can easily show this quantity. So this is the quantity which is there in the right hand side of the equation, and it is clear that this quantity T infinity minus T wall is there in both left hand side and right hand side. So if you just put this and simplify, what you are going to get finally, it is ddx of integration 0 to delta t u into 1 minus theta dy, which is equal to alpha into del theta del y at y is equal to 0. So this particular equation is what is called energy integral equation. This is energy integral equation. Okay. Now what will be our next step? The next step is that we will assume a certain approximate velocity profile. So we'll assume some approximate velocity profile of u, and we'll approximate velocity profile of theta, and using the approximate velocity profile, if we do this integration, it is possible to find out the thickness of the boundary layer, and hence we can find out the local Nusselt number and the average Nusselt number, and hence the heat transfer, convective heat transfer coefficient, and finally the net heat transfer. So let us see how can we do this. So approximate velocity and thermal boundary layer is required. So for the case 1, let us consider case 1 where it is a situation where Prandtl number is much less than 1. The practical fluids, you know, these are the liquid metals. Okay, they are in the order of generally 0.01 or 0.03 like that. Okay, so in that order, so much less than 10 to the power -2 order. This is actually the order of magnitude of the Prandtl number of these quantities. So practical liquid metals. Now for them, if you draw the temperature and the velocity boundary layer, you can see the velocity boundary layer. This is what is the velocity boundary layer, and this is what is the thermal boundary layer. So it is clear that the thermal boundary layer thickness is much larger than the velocity boundary layer thickness. Okay, so what we can do here is that, and it is quite clear that if you see the we are going to analyze everything within the thermal boundary layer. Okay, so our domain is the thermal boundary layer. So if you want to see the velocity profile inside the thermal boundary layer, say at this location, you observe the velocity is uniform almost all over this thermal boundary layer. Only a few portion which there is a significant velocity gradient, that is within the velocity boundary layer, but majority of the part within the thermal boundary layer, this u is basically u infinity. Okay, so this is the situation occurs when Prandtl number is much less than 1. So what we are going to do that in our case, the equation is basically 0 to delta t u into 1 minus theta dy is equal to alpha del theta del y at y is equal to 0. We need not to consider u separately. Okay, definitely if the situation is Prandtl number much greater than 1, in that case definitely you also have to consider the u by u infinity as function of y by delta. So that velocity profile you have to approximate. But at least for this particular situation, which is a simpler one, since the velocity is u infinity everywhere, if the thermal boundary layer thickness is very large, then this u all over this boundary layer we can consider almost u infinity. So this will become a constant, and that can be taken out easily. So for this case only, you can write this as u infinity, which is coming out, and what remains is d dx of integral 0 to delta t into 1 minus theta dy alpha del theta del y at y is equal to 0. Now, so theta you have to approximate. So exactly in a similar way as we have done in case of velocity, approximate velocity profile. So you can write this theta is function of y by delta t only, and that is a third order polynomial. So something like a0 plus a1 y by delta t plus a2 y by delta t square plus a3 y by delta t whole cube. and you can use the boundary conditions, like 4 boundary conditions actually required to solve these 4 coefficients, and you can use the boundary condition like at y is equal to 0, at y is equal to 0, theta is equal to 0. Okay, and at y is equal to delta t, theta is equal to 1. Remember, what is this theta? That is t minus t wall by t infinity minus t wall. So when y is equal to 0, temperature is the wall temperature, so t wall minus t wall, so that is why theta will become 0. Y is equal to delta t, t will become t infinity, so t infinity minus t wall divided by t infinity minus t wall, that is 1. At y is equal to delta t, the slope is also 0. Del theta del y is 0, which is quite obvious because there is no velocity gradient after the edge. And on last equation, boundary condition, we can write that y is equal to 0, del 2 theta del y2 is equal to 0, and that will be observed from the equation u into del t del x plus v into del t del y is equal to alpha into del 2t del y2. Okay, so this is what is the thermal boundary layer equation. Now at y is equal to 0, is u is equal to 0, we know. At y is equal to 0, because of no penetration, we know v is also 0. Okay, so definitely del 2t del y2 has to be 0, which actually means that del 2 theta del y2 then also has to be 0. So these 4 boundary conditions, if you apply and do the algebra to solve this a0, a1, a2, a3, you ultimately end up with that a0 will become 0. You will find that a2 will become 0 and a1 will be 3 by 2 and a3 will be equal to minus half. So your final solution will become 3 by 2 into y by delta t minus half of y by delta t whole cube. So this is an approximate velocity profile considering third order polynomial. So now using this velocity profile, you can now put this value of theta in the energy equation, energy integral equation, and you can estimate delta t and hence the local Nusselt number. So if we put that, if we do that, then what you are going to get is integration 0 to delta t. It is u infinity that will come out into 1 minus theta into dy is equal to alpha del theta del y at y is equal to 0. And what is our theta? The approximate temperature profile is 3 by 2 y by delta t minus half y by delta t whole cube. So to do this integration part, what we are doing is that let us consider y by delta t is equal to eta. So dy will become delta t into d eta, and the limit of integration as y from 0 to delta t, which implies eta will be from 0 to 1. Okay, so if you just put these values here, what you are going to get is that integral 0 to 1, then 1 minus theta is minus 3 by 2 eta plus half of eta cube d eta, and this delta t will be there. So okay, so in this equation actually ddx is there. I forgot to write ddx. So ddx of this quantity along with this delta t will be there. So I have just taken delta t out, and this quantity is basically a number, okay, and u infinity will be there. And here in the right hand side, del theta del y at y is equal to 0. If you differentiate this quantity del theta del y, so del theta del y at y is equal to 0 is definitely, it is 3 by 2 into delta t, okay, because that y square, if you put y 0, that part will not be there. So 3 by 2 delta t. So alpha will be multiplied with that. So 3 into alpha by 2 delta t will be in the right hand side part. And if you do this calculation, what you are going to get is d delta t dx into, what is that number? It is 1 minus 3 by 2 into eta is what? 1 by 2 plus half, and eta cube, that means 1 by 4. Okay, so that is equal to 3 alpha by 2 delta t. Now if you do this calculation, what you are getting, its LCM will be 8. So 8 minus 6 plus 1, so it is 3 by 8 basically. Okay, so if we just write the result, so it is 3 u infinity divided by 8 d delta t by dx is equal to 3 alpha by 2 delta t. Okay, so it is clear that this 3 will cancel and 2 will cancel with 8 by 4. So what remains is that delta t into d delta t. So let's go to the next page. So this delta t will go in the left hand side, and it will be delta t d delta t. So delta t d delta t, and let all other terms in the right hand side. So that will be what? That will be 4 alpha, this 4 alpha by u infinity by u infinity. Okay, so that will be 4 alpha divided by u infinity into dx. Okay, so 4 alpha by u infinity into dx. Okay, now if you just do this integration from when x is equal to 0, as you know delta t is 0 at x is equal to any x, say this is delta t, which is the delta t at that x. So it will be delta t square by 2 in the left hand side. In the right hand side it will be 4 into alpha, you know, is that k by rho cp, and u infinity is there and x will be there. Okay, so what is delta t square? You are getting that delta t square is equal to 8 into you can write one Reynolds number in this way, rho u infinity, and better you divide both side by say x square. If you divide both side by x square, so here one x is there, another x square will be there. So basically it will become ultimately 1x at the denominator. So that x we are writing, and take one extra mu, so that you have to adjust at the denominator. K is already there in the top, and one cp is there, so put that cp here. Okay, so this we are getting, and if you see, this quantity is nothing but what? This quantity is nothing but 8 into Rex to the power minus 1 and Prandtl number to the power minus 1. So delta t by x, this particular quantity is basically what? That is root over 8, that is root over 8 into Rex to the power minus half into Prandtl to the power minus half. Okay, so now you can observe one term is coming, which is the product of the Reynolds number and the Prandtl number, and that particular term is called the Peclet number, PE, or the Peclet number that we have already discussed. So this one is the local Peclet number. So sometimes you can also written this as in terms of a local Peclet number. That means root 8 into Peclet x to the power minus half. Okay, so this is what is delta t by x. Now our final objective is definitely to find out what is local Nusselt number. So for that, what we are going to do, we are going to use the relation that we know is that at the layer which is in direct contact, definitely that is the pure conduction taking place. So you can use the Fourier's law, minus k into del t del y at y is equal to 0, and that heat flux must be equal to, according to Newton's law of cooling, is h into T wall minus T infinity. Okay, so this we already know. So now here you just convert this T in terms of theta if you want to write. As you know, theta is T minus T wall by T infinity minus T wall. So it will become k into del theta del y at y is equal to 0, and it will be multiplied by T infinity minus T wall. Okay, T infinity minus T wall. It will be multiplied by T infinity minus T wall, but one negative sign will be there. And here it is h into T wall minus T infinity. So negative of T infinity minus T wall will cancel with T wall minus T infinity. So what remains is, it is basically k into del theta del y at y is equal to 0 is equal to h. Okay, and now already we know the expression of theta. So del theta del y at y is equal to 0, we know that del theta del y at y is equal to 0 from the approximate velocity profile, that theta is equal to 3 by 2 y by delta t minus half y by delta t whole cube. So del theta del y at y is equal to 0 is nothing but 3 by 2 delta t. So if you just put that value, so it will become k into 3 by 2 delta t, which is equal to h. So what is Nusselt number? So local Nusselt number nu x is nothing but h into x divided by k. Okay, so already we know the expression of h. You just put here in this expression. So it is 3k by 2 delta t, that is what is h. Then it will be multiplied by x and k. Okay, so that is what is the local Nusselt number. So you see that this k will cancel, and the term is basically 3 by 2 into 1 by delta t, sorry, x by delta t. And already we have calculated what is delta t by x in the last page. As you can see that delta t by x is equal to this quantity. So definitely x by delta t will be just opposite to this. That means 1 by root 8 into Peclet to the power, or Rex into Prandtl, that to the power plus half. Okay, so you just put that value here. So multiplied by 3 by 2 will ultimately lead to the local Nusselt number. So nu x is coming what, 3 by 2 divided by root 8 into Reynolds number into Prandtl to the power plus half. Okay, now if you simplify this, that is 1.5 divided by square root of 8, which is coming 0.53. So 0.53 Rex into Prandtl to the power half. Okay, so this is what is the expression of the local Nusselt number that we are getting. But remember, this is the approximate solution. If you want to compare with the actual solution this value, this constant is not 0.53, it is 0.565. So actual solution is nu x is equal to 0.565 into Peclet to the power local Peclet to the power half. Okay, so this is the actual solution, but this is the approximate solution that we have described here. But remember, we can apply this formula when the Peclet number, when the Prandtl number is very low. Generally, if the Prandtl number is less than 0.06, then we can apply this relation. Okay. So this is the way we can solve the problem related to that. Definitely, we have only considered the situation if the Prandtl number is much less than 1. Prandtl number is equal to 1, that we have already covered the exact solution from the Reynolds analogy, that if Prandtl number is equal to 1, then the local Nusselt number will be equal to 0.332 into Reynolds number to the power half. So we have already seen that result for Prandtl number is equal to 1. Now what remains is that if this is for Prandtl number is much less than 1, for this relation, this is for Prandtl number is equal to 1. For Prandtl number, if Prandtl number is much greater than 1, in that case, if you do the similar analysis, if you do this approximate velocity profile and thermal temperature profile and do the calculations, in that case definitely the calculation will not be so easy. Lot of algebraic manipulations will be required, and if you can do that, then you will find that it will ultimately come that nu x will be equal to 0.332 into Rex to the power half into Prandtl to the power 1/3, and this result is valid for Prandtl number much greater than 1. So ultimately what we can conclude is that if the Prandtl number is greater than say 0.6, then we actually can use this particular formula, because if Prandtl number is there in this expression, as you can see, Prandtl number is 1. So if you write that 1, then ultimately this is also satisfying this condition, because the Prandtl number is 1 at that time. So generally this equation is valid between Prandtl number 0.6 to 60 at least. Okay, so this is what is the relation. So finally, what if we conclude the results that we got here? These results you are going to get if you do the rigorous analysis, that means this integration and all that, then you are going to get, for this case we have only discussed the situation if the Prandtl number is much less than 1, that situation we have discussed, and in that case you will find this is the relation. Okay, so I think we end this discussion here. In the next lecture we will see some of the very important relation, those you require to be remembered, because it's not that all the relations we will be able to derive. Many relations are suggested, many relations actually came from the experimental analysis. So I will show you some of the very important results through which you can solve these problems. Thank you.